Hey everyone. So thank you for joining us for this 1 hour session on data visualization. I'll start by introducing myself. My name's Nicole, and I'm a master's student specializing in data science at this university after having done a biomedical science degree. And I'm co-teaching this session with Sahil, another master's of data science student as well. So this workshop assumes that you have a basic understanding of Python syntax, the Jupyter environment, as well as some familiarity with pandas, a Python package used for reading and manipulating structured datasets. So if you don't have this knowledge, that's okay. We taught a workshop last semester, which we've linked here, that covers those topics. So check those out before returning to this workshop. So today we'll teach you the syntax of plotting charts and visualizations with two Python plotting libraries, Matplotlib and Seaborn. So Matplotlib is kind of the basic plotting library of Python, and Seaborn is one that's built on top of Matplotlib and is more sophisticated, handles more complex visualizations better, and also uses fewer syntax than Matplotlib. We hope that by teaching you these two libraries, you'd have at your disposal two tools that can pretty much together handle any static visualization job. So let's get right into it. For this session, we're using a Google Colab Notebook, which is basically a Jupyter notebook that's running on a Google virtual machine in the cloud. So you can download this notebook to your system and run it there if you have a Jupyter installation. You can download by clicking on File, download.ipynb, which is the Jupyter extension. And yeah, your Jupyter environment might look slightly different to mine because I applied the dark theme onto my notebook here, but this is pretty much what you should see. Running it here on Google Colab allows everything to be reproducible exactly between your system and mine, and we avoid package and version conflicts this way. So let's first make sure that your Google Colab Notebook is active. And it is active when you see these two bars in the upper right-hand corner of your notebook here. If it's inactive, you'll see a prompt to connect, and you have to click on that to activate it. We then have to make sure that can access the dataset. So this folder, which would have been linked to you, you could add a shortcut to your Google Drive. So clicking on that option right there. And we run this cell to mount our Google Drive or connect that Google Drive folder to this notebook. So I've already mounted mine, but what you should see on yours is a link, and you click on that link and it takes you to a Google authentication page. And once you sign in successfully, it'll give you a code, which you then enter onto the output down here. And if successful, it'll say that your Google Drive has been mounted successfully to this notebook. We then need to change the folder that we're working from to that containing the dataset. So sometimes you mount your drive, but you're not actually in this folder yet. So we have to change that into that folder. And we could do that by first finding out where that folder is within our drive. So mine is named DataVis Workshop 2020, and I can click on that and copy the path to that folder and paste it to this path variable. I run that cell, it stores the path to that variable, which we then use with a change directory command here to change into that specific folder. Then we double check that we have the dataset within our current working directory by running the list command, and we see that we do have it here, the heart.csv file. So today we're using a very popular dataset called the UCI heart disease dataset. So this dataset is used for exploring what factors contribute to heart disease, and there are factors ranging from personal attributes like a person's age, biological sex, to behavioral attributes like how much exercise they get, and to physical attributes like blood sugar levels, for example. The target, or the thing that machine learning tries to find out from this data set, is the presence or absence of heart disease. And throughout this session, we refer to the target interchangeably as a label, and we refer to the 13 other attributes in our data set as features or factors. So let me just run this helper code here. You don't have to worry about the details, but basically what it does is change the figure sizes and font sizes so that they're visible enough for you. Give me an error because I haven't imported the necessary libraries, so I'll do that and run this again. So yeah, this step is where we import libraries that we need for this tutorial. So pandas and NumPy for manipulating data, and our two plotting libraries, Matplotlib and Seaborn. Oopsies, Seaborn here. So we abbreviate Matplotlib pyplot as PLT and Seaborn as SNS, so we don't have to write the full names of those packages when calling functions or attributes within those packages later on. So first things first, we read in our data into a data frame that we can work with within Python. So you can see this big block of output here. That's just the documentation for a function within pandas called read CSV, which is responsible for reading in CSV files. Okay, so we could access the documentation of any function within a Python library by calling the help function. So just delete this. We read in our data frame and store it to a variable called df. Then we might want to find out how many rows and columns of data we have. We could do that by calling the dot shape attribute on the data frame. By the way, to execute cells without clicking the play button, you just go Command Return if you're using a Mac, and Control Enter if you're using a Windows computer. So we see that we have 303 rows of data and 14 columns of data. And it's 14 because of those 13 attributes that we have here and one target. Now, we might want to have a look at what the data looks like. So to just get a bird's eye view of our data frame, we use the .head command. What that does is returns the first few rows of your data set. So if we don't pass in a number, it returns the first 5 rows by default. But if we want the first 10 rows, for example, we just pass in 10. So what we have is a data about 303 individuals, and each individual is described 14 ways. We also see that all columns are numeric, with most of them having integers, and a column here having decimal point numbers. So we'd often want summary statistics of our data just to gauge what baseline values we're working with. And to do this, we can call the .describe function on our data frame. Now, summary statistics like the mean, median, standard deviation can be derived if our data is numeric, which it is. But what if our data is categorical? How can we look at aggregate statistics or summarize our data in some way? If we look at the documentation for describe, we could see, so I won't demonstrate that, so it'll be like huge output returned here. But we'll see that we can pass in a value to the include argument, indicating whether we'd want statistics for just the numerical data or the categorical ones too, or both. So we can simply pass in an all parameter, which we do here to include both. We won't have time to look at the entire output that's giving here. So we focus on one column for now, like the age column here, for example. And in the age column, we see that we have 303 values for that column, and that's including duplicates. And it's the same for all of the other columns in our data frame. And that makes sense because 303 is the number of rows in our whole data set. So then we go down the summary statistics generated by Describe, and we see that the average age of individuals in our data set is 54 years old, and the standard deviation, or how much individuals generally vary from this average, is 9 years old. We have the youngest person in our data set is 29 years old, and 77 as the oldest. And we have our quartiles here. So our 25th quartile, 50th quartile, 75th quartile, which essentially means, if we take the 50th quartile, half of the individuals in our data set is aged 55 and below. Okay. So another useful attribute of a data frame is what data types it has. And we can find that out by calling the .dtypes attribute. This is useful because certain algorithms and visualizations might cater to data only of a specific type. So we can see here in the output of that what we already know, basically, that most of our data is encoded as integers, and we have a column here that's encoded as a float or a decimal number. So just a quick note here. Some of the columns, despite being categories, might be, or are, in our case, encoded as integers. So the biological sex column, for example, refers to either male or female, but here it's encoded as 0 and 1 in our data frame. In drawing a visualization or in any downstream analyses that we might do later on, we have to treat it as a categorical variable still. And so it's good to be mindful of the fact that although it's a number, or looks like a number, it might represent a category later on. So how did I know that the sex variable is encoded as 0 and 1? Well, I can call a function that tells me the unique values present in a column. So I first supply the data frame name, supply a column name after that to restrict the function to that column only, not the whole data frame, then call the .unique function. And it gives me 1 and 0 as outputs. So now that we've looked at how to eyeball data frames, let's start visualizing and looking at trends within the actual data. So the first plot we'll cover is a histogram. What it does is show you the distribution of a continuous numeric variable. So this is a useful tool for when you'd want to do statistical tests later on, and these tests assume that your data fits a certain distribution. So you could check that distribution with a histogram. Syntax for creating the plot that you see here is in this code block. So you have the .hist function with an argument of the column that you want to visualize. You can add a title, like we did here, with a .title function, X and Y labels with these functions, and the .show command isn't useful in Jupyter, but in environments other than Jupyter, where you want to make sure that your plot shows, you'd want to add that in. So in this histogram of the resting blood pressure, we can see that the distribution is skewed to the left, with most values occurring in the lower end of the spectrum. And we could see a peak here corresponding to the mean of the data set, around 130 milligrams of mercury. And if we scroll up to our summary statistics column, we see that indeed the mean is around 131. Okay. So we could see the distribution of a numeric variable that way. How about a categorical variable? We could roughly eyeball the counts for each level of a categorical variable and kind of visualize a distribution in our head doing that. So if we call the value counts function on the chest pain column, which is a categorical variable with 4 levels, 0 to 3, we see here the number of counts for each level. We see that the distribution is slightly skewed, with, again, a lot of values occurring with low chest pain, so 143 there, and the least amount of values occurring with high chest pain. So that works for a variable with a low number of levels, but what if it has a high number of levels? It gets very tedious to kind of work it out in your head. So then you have to plot it that way. We could do that plot through a histogram, and this works because the CP variable is, again, encoded as a number, although it's a category. And so calling the hist function and passing in the just pane column gives you this plot. But as you see, this plot looks weird, because it has this big gaps in these intermediate values here. So how do we make it look better? We can essentially just use a bar plot. And a bar plot is a type of plot that compares a categorical variable in the x-axis to a numeric variable, which is either discrete or continuous on the y-axis. So in this example, we use the other library, Seaborn, and we use a count plot function, which is essentially a bar plot modified to display counts of a categorical variable. As you can see here, we could still use Matplotlib functions on Seaborn plots, but Seaborn gives or already automatically provides axis labels. And I believe Sahil will talk later on about how to customize this to your own labels. And if you kind of draw a smoothing line, you could see that it is left skewed, just like the distribution of resting blood pressure here. Cool. So here I just demonstrate another bar plot comparing chest pain to a numeric variable, which this time is continuous. For this example, the continuous variable is the maximum achieved heart rate. So notice that the syntax is changed from dot count plot to dot bar plot, which is the actual syntax for drawing bar plots in Seaborn. Also notice the error bars generated here. Bar plot actually by default gets the mean of a continuous variable in each categorical group. So category 0 here has a mean maximum heart rate of 140, varying by about, let's say, 5 units up and down from that. If we wanted the median, we can pass in a median estimator to the dot bar plot function instead. If we look at the documentation for bar plot here, we see that one of its arguments is an estimator function, which is a mathematical function used to calculate a statistical kind of measure of central tendency, so either a mean, median, or mode. And by default, it gives you a mean if you don't specify anything else. Okay. Now, what if we want to visualize two continuous numeric variables against each other? So we use scatter plot for that. The syntax is using Matplotlib and calling dot scatter. So each dot in the resulting output here is a row in our data set. And we can see here, if we kind of interpret what this plot shows, we see a slight positive association between our two numeric continuous variables, which are cholesterol levels here in the y-axis, resting blood pressure here in the x-axis. So you could draw a line on the scatter plot as well, a regression line, for example. So before I pass it on to Sahil, I just want to leave you with the fact that plots are very customizable. So apart from adding titles and axis labels, which we've shown earlier, we can add annotations to the plots. We can group the visualization by another variable. We could split a plot into multiple plots. And as I mentioned, we can change our estimator for bar plots or any plots that do aggregate statistics. So I just included examples of some of the customizations I've mentioned here below. And I'll quickly talk through some of them, but I won't really explain anything. I'll just leave you to see how the syntax works in your own time. And I'll pass it on to Sahil immediately after. Okay. So this first plot basically shows grouping. It shows our chest pain variable grouped by another categorical variable, which is the sex variable. This plot then shows annotation where we kind of grab a specific value, in this case, highest cholesterol value, and try to point to it in our data set with an arrow. And finally, last customization that I want to leave you with is a change in estimator here. So instead of doing a mean, we do a median. You can see that the error bars look different now. Awesome. Now I pass it on to Sahil to talk about more plots.
Hi everyone. We have seen now how to read in the data into Python, make some basic visualizations such as histogram and bar plots. The next thing we'll be moving into is what is called as the box plots. Box plots are basically visualizations of the 5-point summary of the data. I'll talk about what the 5-point summary is, but before that, let's just take a look at what exactly the box plot function requires as the input. Okay, so the basic requirement is an array or sequence of vectors. What this means is that you need to give into one column of your data set, which has to be of the form numeric and has to be continuous. So we'll just select the resting blood pressure to build the box plot on. So if I do run the box plot function, I get a nice plot over here. This plot is built on the 5-point summary. What exactly the 5-point summary means is that it will use 5 different points to build these 1, 2, 3, 4, and 5, these 5 lines. Okay, so it uses these 5 points over here, the minimum, the 25th percentile, or what is also called the first quartile, the 50th percentile, or the median of the data, the 75th percentile, or the third quartile, and the maximum value. Okay, so this lowest point of the data set of the box plot is your minimum. So that's at 94 over here. So this point corresponds to 94. The maximum is at 200. That's over here. So this is a single point at 200. This lower part of the box plot, this lower base of the box plot, this is the first quartile. So your 25th percentile, which is at 120. The top of the box, this is the third quartile, which is at 140. And this orange line at the center is the median or the 50th percentile. So that is at 130. So this is basically the box, and it is accompanied by 2 whiskers, one on each side. And the length of the whisker is defined or just generated by using the formula 1.5 times the interquartile range. The interquartile range is simply the difference between the third quartile and the first quartile. So in this case, the third quartile is at 140, or you can just check it from here. It's at 140, and the first quartile is at 120. So the difference is of 20, and 1.5 times of 20 becomes 30. So the length of each whisker has to be 30. So if you look at this whisker over here, it starts at 140 and it goes right up to 170. Similarly, on the other side, this whisker starts at 120 and it should go 30 points underneath. But if you check, this is at 120. If you had to go 30 points below, it would go up to 90. But the lowest value in the data is 94. So it doesn't really make sense to go beyond the minimum value of the data set. So the whisker just stops at 94. Now there are some points beyond 170 over here, these points. They are just left out as how the original points would look on the data set. That is because by a general rule, whatever lies beyond the whiskers could be potential outliers. So and it's not necessary they are outliers, but they potentially can be one. So it's better to just check into it. So outliers are basically just extreme points which will uh, create a little bit of irregularities when you are trying to build a model, and they may be just points that have been recorded incorrectly. So sometimes when you look at the age variable, you might have values that go beyond 100, or not just 100, they may go beyond 120 or something like that. Those are just incorrectly recorded points. So it's just a good idea to take a look at why they are there. So that's basically how a box plot is built. This y-axis is just the different values in your resting blood pressure, and on your x-axis for just a single variable, you really don't have any label because it's just this particular variable. Now you can have certain options when you're building a box plot. The basic option that you might end up using a few times would be that of a notch. So this notch, it adds this notch over here. So in our data set, it really looks like the notch is exactly at where the median is supposed to be, but it's not at the median, it's at the mean of the data. So if you look from this table again, the median is at 130, which is this orange line, and the mean is at 131.6, which is just so close to it that it feels like it's coinciding. But if I just try to zoom into this, let's see, it's a little above the orange line. So the notch is just showing you that the mean of the data has to be at this point. Next, there are other options like you can change the uh, color and marker for the outliers over here. These outliers, they were not filled. There were circles which were not filled, but now I fill with red color. In order to do that, there is an option in the box plot, flyer props. You can just mention. So what you need to provide here is basically a dictionary. Dictionary is basically just a collection of key and values. So over here, I created a dictionary which is called the red circle, which is telling that I'm creating a dictionary where the marker face color is R implies red, and the marker type is O. O is basically a circle. There are many other colors available in Matplotlib and many markers available. You can just maybe check the uh, list out. You have a link over here to check different colors. For markers, the general ones are you can have an X, or you can specify S if you want a square. So it just changes. But if you actually put in X, there is nothing to fill in. So it's like you are going to have X, but it's just going to be a black X. If I may specify a square over here, it will just make a square which is filled in with red color. So you can do fancy things with the outliers, or if you don't want the outliers altogether, that can be done as well. So there is another option, show outliers. So it's basically just to show outliers. By default, it is always set to true, so you always get the outliers. But if you set it to false, um, you don't have the outliers now. So again, the length is 30 units on this side, so it's going up to 170, and it's going up to 94 on the lower side. Uh, Another very useful thing that you can do with box plots is to make the vertical box plots horizontal. So there is an option over here called the word. You can just set it to false. So by default, it's always true. If you set it to false, you will get a horizontal box plot. Horizontal box plots are useful when you want to compare the box plots with the histograms. Box plots, as I said before, are one of the most informative visualizations. You can get a lot of ideas about how the data is. So, and you can uh, figure out if there is any skewness in the data, where the mean and the median is. If the mean is on the right of the median, the data generally has some right skewness. Plus, you have some potential outliers towards the right. So that's again an indication that the data is going to be right skewed. So if you want to just check that how does the box plot compare with the histogram, you can make a box plot and then you can just make another histogram with it. So now it's like easier to compare the distribution and make more sense. So if you can just project every value. So your minimum value is over here at 94. This is your first quartile, so that's 25% of your data lies to the left of this value. This is your median over here. Again, this is your third quartile. So you can see that most of the data, is going to be concentrated over here. And these outliers over here represent the skewness in the data over here. Another thing you can do is you can just set the notch to true. So that will actually also show you where the mean of the data is, which is sometimes helpful when you're making the histogram. So you can just project the mean. It's going to be somewhere over here as well. Now, I mean, since the median and the mean are not that far from each other, it's like there is a hint of the data being pretty well distributed on the normal scale, but still, I mean, you have some skewness over here. So, so that was a univariate box plot using just one continuous variable. You can build box plot using more than one variable, but the condition is that one variable has to be continuous and the other variables will have to be categorical. So in order to do that, let's use the sex from the data set. So originally the sex is like 1 for male and 0 for females. We'll just change that to males and females in the actual data set. So it's just easier to understand what the box plot is explaining. So once you do that, you can just check over here when you convert it to male and female, you might get some warning that it's trying to set the new value on a copy of the data set, but you don't really need to worry about that because you are assigning these values to the original data set at the end. So the original data set does get updated. And if you just see how the data set looks now, you can see that this particular column has been changed from ones and zeros to males and females. Now, if you want to use two variables in your box plots, you just you it can be done using Matplotlib, but it requires a longer piece of code. It's easier to do using Seaborn. Seaborn is much more user friendly when it comes to working with multivariate or bivariate plots or multivariate plots. So in Seaborn, you just need to specify that on the x-axis you should have your categorical variable, which is sex, and on the y-axis you can have your continuous variable, which would be the resting blood pressure. And it's always a good idea to have your labels and titles so that you know what you're plotting and what you're plotting against what. So this is what happens now. Previously, we just had one single box plot for the resting blood pressure, but now you have two different box plots. One is for the males and one is for the females. So this gives you an idea if you had different groups in the data set, how is one variable for that particular group and how is that same variable for another particular group. So, I mean, from this thing, you can actually see that there isn't a lot of difference. It's still like the median. Actually, most of the statistics are pretty similar for them, except for maybe this in the females, the maximum value is a little higher than the ones in males, but overall, I think the distributions are pretty similar. Now you can add another variable, but it has to be a categorical one. So if you want to do that, if let's say I wanted to add another variable to this. You already have sex on your x-axis and the resting blood pressure on your y-axis. What you can do is you can use the U option in your box plot from Seaborn. What it does is it splits each of the box plots into two different box plots, and it uses my target. So my target is the outcome, which is if a patient has heart disease or if he does not have a heart disease. So it will split the males and females into two more box plots each. one with males having heart disease, one with males not having heart disease, one with females having heart disease, and one with females not having heart disease. Yeah, so there you go. That's how it looks. So we already had the resting blood pressure and the sex over here, but now you have a target. So these two box plots here have been further split into two box plots each. So what it basically means that this particular box plot, the one in blue, it implies that this is a distribution of the males who do not have a heart disease. This orange one is the distribution of males who have a heart disease. Similarly, for uh, this is the distribution of the females who do not have a heart disease, and this is the distribution of females who have a heart disease. Now, over here, you can see that for the males, regardless of if they have a heart disease or if they don't have a heart disease, the distribution is quite similar. But for females, there is some difference. The females that do not have a heart disease have a little higher blood pressure than the females that do have a heart disease. So something like this might come in handy when when you want to start your modeling, or when you're just trying to do some preliminary or your exploratory analysis. So that was all for box plots. So in box plots, you can either have one continuous variable, or you can have one continuous variable and several categorical variables. But most of the times you would want to compare two continuous variables with each other. And in order to do that, you would have to use the scatter plots. So scatter plots basically plot the relation between two continuous variables. The format of scatterplot is similar. You provide your x-axis and you also provide your y-axis. You can provide a categorical variable, but it really won't make any sense to have a categorical variable in a scatterplot, because you'll just have either rows of observations. So it's like in categorical variables, the observations will jump from one value to another, and you won't have anything in between. So it just really doesn't make any sense to have a categorical variable when you're building these scatter plots. So if you have two continuous variables, this is how your scatter plot should look like. The scatter plot will actually help you to see if there is any trend or pattern in the data. Now, if you look at this one, you really don't see anything, but sometimes you might just find out some important information, and that might be helpful when you're building your models. Again, there are many different options that you can use in scatterplot. Now you can use categorical variables to separate the data. So in this case, it's not going to change the plot. It's just going to mark the different observations in different colors to show you that these observations are males and these observations are females. So this is basically how it ends up looking. The plot is exactly similar to how it was before. The only difference is that the males and female observations are separated by color. There are many more options that you can have. So you can change the size of the um, points over here based on the different groups. So you can have a smaller size for male, smaller size of the dots for males and larger size of the dots for females. You can change the marker type, and there's also an option called alpha. Alpha basically is the opacity of the points on the graph. By default, the value of alpha is 1. What it means is that by default, these plots are completely opaque if there is, or these points are completely opaque. If there is one point behind another, you can only see the point that is on top. You cannot see the points behind them. So if you want to do that, let me just set this to 1 for now, so we can see the difference later. So if I make this plot, you just have different sizes for males and females right now, and the markers will be set to X. So the marker is set to x. It really doesn't make a lot of sense to have alpha equals to something, some lower value of your marker is x, because you can pretty much see what values lie behind the ones on the top. But let's say if your marker was something like a circle. In that case, if you see the plot now, yeah. So if you see the plot now, the okay, so you have the color is based on the target. So color is based on if the uh, person has heart disease or not, and the size is based on your sex. So the males have the ones with the larger size, and the females are the one with the smaller size. So if you look at these uh, points now, so if you consider this particular point, this is going to be a male who has a heart disease. This one is going to be a male who does not have a heart disease. This is going to be a female who has a heart disease, and a small blue one over here is a female who does not have a heart disease. So if you look at these points over here now, those are a cluster of a lot of points. So there might be some data behind that cluster, which will become visible if you change the value of alpha, let's say from 0.1 to, oh sorry, from 1 to 0.7. So now the opacity has reduced, making the uh, points a little more transparent. So you can see that there were a few points. There was yeah, over here. You can see that there was a big blue circle over here, within which there was a very small orange circle. Again, it was similar over here. There are a few points over here as well, and there certainly are a few points behind this, which were not visible before, but now since you reduce the opacity of the points, they become visible. So this alpha might come in helpful if you want to see where the a few hidden points are uh, behind some other points. So it just might come in handy sometime. So this was a scatter plot for just two variables, but uh, actually when you start modeling, you want the scatter plot between all the continuous variables. So like you want, so in our case, we have about 8 or 9 continuous variables, and we would like to see the scatter plot between all of them, right? So you want a scatter plot between a variable 1 and 2, between 1 and 3, between 1 and 4, between 1 and 5, similarly 2 and 3, 2 and 4, 2 and 5. You can do that manually. You can just make several different scatter plots, but it will just take you a lot of time to do that, and it will be difficult to compare those scatter plots with one another. So the way to do that is to use a scatterplot matrix. A scatterplot matrix will create a huge matrix of scatterplot between all continuous variables. So it will only use continuous variables. It will not use the categorical variables. So I'll create a smaller subset of the data with mostly all these continuous variables, and I'll just include one categorical variable to show you that by default the function just ignores that variable when building the scatterplot matrix. So let's take a look at what the data set looks like right now. Yeah, so we just have these 5 continuous variables and one categorical variable over here. So now to make the scatter plot, we use this pair plot. So if I run this function on the entire on this entire data frame, I'm using the entire data frame. I'm not specifying what columns I want to use. So it is building a plot of uh, five uh, 5 by 5 matrix. So you have 25 plots in all. Uh, let's start on the y-axis first. You have 1, 2, 3, 4, and 5. On the x-axis, again, you have the same 1, 2, 3, 4, and 5. Okay, so you have got 25 scatter plots for 5 variables. Now, if you look at the diagonal elements, they are all histograms. That is because the way the plot is set up, over here you have age on your y-axis, and the x-axis over here is age as well. Okay, so this basically is a plot between age and age. So if you could just visualize, if you had a plot between that same variable, it's always going to be a straight line. So it doesn't really make sense to build a plot. Instead, it just gives you the distribution of that variable. So all these diagonal elements are plots between the same variable. So it's just a histogram instead of having this straight lines. And all the plots in, let's say, this lower diagonal part are exactly the mirror image of what's there in this upper diagonal part. So for example, if you look at this plot, this has the resting blood pressure on the y-axis and age on the x-axis. Okay, so and the corresponding plot to this is this one, where now you have age on the y-axis and resting blood pressure on the x-axis. So this is just like a flipped image of so this plot is just a flipped image of this one. So you're just changing the axis, but it's the plot between the exact two same variables. So you don't need to like interpret all these plots. You just need to interpret at least one side of the diagonal. So if you are able to look at or understand one side of the diagonal, the other side explains the exact same result. And you have for every row you have the column sorry, the y-axis specified over here, and for every column you have the x-axis specified. So for example, this is the cholesterol level versus the age. We get the age from here. This is the cholesterol level versus the resting blood pressure. Similarly, you have uh, old peak on your y-axis for all these plots, and you have several different values like age, resting blood pressure, cholesterol, and this is I think the heart rate, maximum heart rate achieved on the x-axis. So just by one function you get all the plots that you require. Again, there are a lot of options that you can give into the pair plot function. So if you want to plot the trend in the data between the two variables, you can just specify kind equals reg. That basically what it does is it fits a regression line between the two variables. So over here, you just had the points. You did not have any line that was specifying what the trend in the data is. But now, using kind equals reg, you get a line in the plot. So you have a line each of the plot, which is uh, explaining what's the trend in the data or how is the data changing when you're moving from the lower values on your x-axis to higher values on your y-axis. If you look at most of the plots, there isn't a strong relation between any of the variables. Maybe the maximum heart rate and the age has kind of the strongest relation, that the increase in age, the maximum heart rate is showing a downward trend. But apart from that, really, most of the lines are really parallel to my x-axis. So there isn't very strong relation. Is something that you can see from this. Another thing that you can do with the plots is you can separate the values uh, for males and females, so based on a categorical variable, and you can have separate lines explaining the trends in males and females for each of the plots. So yeah, now if you look at this, you don't just have one single color for the entire data set. It's separated by males and females. So blue ones are the males and orange ones are the females. And not just that, but you can see that uh, there are two lines now. So there is an orange line and there is a blue line. So the blue line is explaining the trend for the males, and the orange line is explaining the trends for the females. Mm, So yeah, these are some of the useful things that you can work around with the scatter plot and the scatter plot matrix. And this really does come in handy when you start working on your data modeling part. Um, Next thing that would be helpful and something that is already based on your scatter plot is using the correlation matrix and making heat plots or heat maps. So correlation is basically the relationship between two variables. So if you look at, let's say, these two variables over here, your old peak and your age. So with the increase in age, there is a slight increase in your old peak. That's what the trend is explaining. Um, if there was a linear increase, so what basically that means is that as my age is increasing, my old peak is increasing by the same amount for every increase in my age. So, in that case, you would have a very linear relationship between age and old peak. So like all the values would be along a straight line. In that case, my correlation would be 1, but that very rarely happens because the changes between the two variables are never going to be that similar. There is going to be some variation in there, and this is the variation. So it's like for all increasing ages, the value of old peak is not increasing by the same value. The change is different, which is why the correlation is not going to be 1, it's going to be less than 1. But the closer the correlation is to this particular line over here, this straight line, the stronger is the correlation. Okay, so if they were really close to the line, the correlation would be somewhere around zero point 0.8 or zero point 0.9. But now they are like spread across, spread across the space, and there are very few values that are actually close to the line. So the correlation is going to be really really weak. Uh, and again, the correlation, it can vary between -1 and +1. If there is no relationship at all, if the spread is extremely absolutely random, the correlation is going to be 0. If there is a positive trend in the data, so with increase in one variable, if the other variable also shows an increase, the correlation is going to be positive. Or if with increase in one variable, the other variable shows decrease. So for example, something in like in this plot where the trend is a downwards one, the correlation is going to be negative. So you can see in this plot that the correlation here is negative, and for most of them it's positive because it's an upward trend. For the correlation between a variable and itself is always going to be 1 because it's always going to be a straight line. If you want to see, we can plot that as well. So yeah, it's always a straight line, and that is why the correlation is 1. Now, once we have the correlation, I mean, it's a better idea to present it as a visualization where you can use heat maps. So heat maps are basically, it's a map where you have, which is color coded. You go from one shade of a color to, or you go from a lighter shade of a color to a darker shade of a color, and you have a scale here explaining what the shades of that color mean. So if you have a very light color, it means that there is a very strong correlation, or the correlation is close to 1. And as the shades get darker, the correlation is decreasing and eventually going on the negative scale. Again, it's like if you look at this visualization, it's giving you an approximation of how strong or weak the correlation is. It's not giving you the values. But if you do want the values, there is an option. It's called the annotate option. You can just put that as true. So if you do put the anode equals true, you get a heat map with all the values printed. Now this makes much more sense. This is not just giving an approximation where the correlation is positive and strong, or very weak, or is it negative, but it is giving you the actual values. So it just makes it more presentable. Heat maps have many more options. You can check using the help. Most of the times, heat map will come into play when you want to uh, present your results of your analysis. They are not that helpful when it comes to the exploratory analysis part. So we might come back to heat maps when we actually talk about the data modeling part. Uh, that was all about the plots that we have in Python, and ones that might be of most help or most use to you. The final part that we want to talk about is that of subplots. So you might want to have more than one plot built together. So you might want to have a matrix of plots, like we have for the scatter plot, but you might want to have a variety of plots that you want to compare with one another. So for example, you might want to compare a box plot with a histogram, like we did before when we were doing the box plots, but we had one box plot built first, then a chunk of code in between, and then the second box plot. Oh, sorry, then a histogram of that box plot. That becomes a little bit tedious when you want to compare multiple plots together, and what you want to do in that case is make subplots. So this is the basic command that you use for subplots. If you do not provide any argument, it will build a single subplot. So that is what we have been doing till now, actually. You have a single plot, which is what is basically a single subplot. And what this function does is it returns back to two particular values. The first one is the figure. The figure is the entire matrix. So no matter how many plots you have, like you have four plots, then that entire matrix of four plots is given into figure, and every single plot is stored in this second variable, which is basically an array of plots. It might be one dimensional or two dimensional, depending upon how your matrix is. So let's start off with the basic one. That's just a single subplot. If you do build a single subplot, it's basically like the previous plots that you have. So I'm just making a plot of between age and resting blood pressure. This is going to build a scatter plot between age and the resting blood pressure with blue circles as the points. So this is what you have. This is what we already had before. This is exactly what happens when you build a single subplot. Now, to build multiple plots or multiple subplots, you need to specify some arguments. So you need to specify the number of rows and the number of columns that you want uh, in your subplot matrix. Now, in case either of your number of rows or number of columns is one, it is it is basically going to say that this is going to be a one-dimensional array of plots. Okay, so it's like uh, you just have one column of plots, or you have one row of plots. It becomes a single dimensional array, and that single dimensional array is going to be stored in this variable, which is called axs. So to access every plot in that array, you will have to provide the index of that plot. So we start with 0. That's the first index or that's the index of the first plot. Then you move on to 1, 2, 3, as many plots as you have. And one thing to note is that over here, if I just comment this out and run the code, I'm just making a box plot on in the first subplot, and then a histogram in the second subplot. So it's going to be a box plot on top of a histogram, because we have two rows and one column in the subplot matrix. So if you just build the plots with the default setting of the system, uh, the title of the plot of the second plot is always going to override the x-axis of the first one, because by default the distance between the two plots is very less. So in order to fix that, you can use the plt.subplots underscore adjust function. In that function, you have a lot of options, like you can specify where the left or where the plot is supposed to be located, or how what should be the distance between two plots when they are one on another, or when they are side by side. So I'm going by default the distance between the two plots is zero point 0.2. I'm just going to make it zero point 0.5. So it will just move the second plot a little lower. So now the title is not overwriting the x-axis of the first plot because we just increase the distance. So you can make a few changes to the other parameters and see how the size of the, or not exactly the size, but how the position of the plot is changing. So yeah, you can just use the help function to see what the default settings are and how you want to change them to uh, mm, fit whatever plot you have correctly in the matrix. And also remember one thing: the plt.subplots underscore adjust, it always needs to be placed right before you start building the first plot. It cannot be placed even before you create the subplot matrix. It has to be placed right before you start building the first plot. Otherwise, it's not. These settings are not going to be applied to the plots. Okay. Moving on. The final thing that we have in the subplots is building a two-dimensional array, two-dimensional matrix, or what do you say, a two by two subplot. So this is going to be build a subplot or matrix where you have two rows and two columns. Now, if you uh, actually check this variable, it's not going to be a single dimensional array anymore. It's going to be a two-dimensional array. So you will have to index it using the rows and columns. So if you want to access the first plot, you'll have to provide 0, comma 0. Then you have to provide 0, comma 1 for the second one, 0, comma 1 for the 0, 1, comma 0 for the third one, and 1, comma 1 for the fourth one. So by using the indexes, you can access any of the plots in the matrix. You just need to remember that the way you're creating your subplot matrix, it might be a one-dimensional matrix or a two-dimensional matrix based on how many number of rows and columns you have. Again, in this, I'm using this plt.subplots underscore adjust. I am just changing the space between the plots just so that they don't overwrite. And over here, I'm going to build a box plot of the resting blood pressure, box plot of the age, histogram of the resting blood pressure, and a histogram of the age. And yeah, so now you get a matrix of subplots where you have all the plots that we wanted, and this becomes so much easier to compare the plots. You can have many more plots. You can have, and you can have just have all the continuous variables with a box plot on the top and a histogram of the same variable underneath it. So it becomes really easy to compare, each plot with another. So subplots might come in handy when you're uh, want to make several plots. Uh, so that was all that we had in terms of making the plots. One final thing that I would like to talk about is the plt.show function over here. We have that function throughout the notebook. Uh, and frankly speaking, this function will not make a difference when you are working in the notebooks. So no matter if you have the function or you don't have the function, you are going to get the plots because the graphical interface of the notebooks works different than the graphical interface on your machine. But if you were running the entire code as a script in let's say some other interface, not as a notebook, but in some other Python compiler. In that case, if you did not have plt.show, the script cannot communicate with the graphical interface of your machine to tell it to open a graphical window to display all the plots. So you will build the plots, but you will not see the plots anywhere. So in case you want to see the plots, and that's always the case. So to see the plots, you will always have to put in plt.show and make sure that the plt.show is occurs only once in your entire script, and that too at the end of the code. So do not put it anywhere in between. Put it right at the end. If you do put it somewhere in between, so or if you have plt.show multiple times in your script, what will happen is that when you build all the plots and you want to display the plots, you will get all the plots that occur before the first plt.show. All the other plots, those plots will build, but they will not be displayed in the graphical window. So you will only get like for this part of the code, you will only get these two box plots, but you will not get these two histograms. So this is what will happen. So just make sure that when you're using plt.show in your script, or even on the notebooks, you in every part you just have plt.show just once and right at the end. So that's it. That's all we have for data visualization. Thank you.